Okay, the two subspaces that you're pretty familiar with are the null space and the range space, the row space. Okay, so you got null space of your transformation, and you have the row space of the transformation. Okay? Then over here, but and we know, and we've said it a number of times. Yeah, no, I'm not even going to say it. We've done it. But every vector in N of t is orthogonal to every vector in the row space. I could say and vice versa, but if it applies to every vector in this space and every vector in that space, it's already stated. Okay? V and W are inner product spaces. Not every vector space is an inner product space. And we can't talk about the orthogonality of these two spaces unless we've got an inner product to test orthogonality with. And what's the condition for orthogonality? Fairly new, so if you don't know, what can you tell me about the dot product of two vectors that are perpendicular?
They end up to 0.
It's 0. The dot product is this times that times the cosine of the angle between them, right?
Yeah.
And the cosine is 0 if the angle is 90 degrees or if the things are perpendicular, right? And inner products just extend the idea of dot product. And we did inner products, integrals, okay? And inner products of function spaces, okay? So we did many examples of that, and that was really, I thought, fairly straightforward, easy assignment. But we'll see. Was that one due today? I don't know if I've seen it yet, but with the document feeder getting screwed up and messing up my whole life, I don't know what I've seen and what I haven't, but I think I'm pretty well caught up in things. Except for that homework of yours that I looked at, but now I can't locate it.
Was it?
It'll turn up, but
Was it bad?
got a huge mess. It was okay.
Okay.
I mean, you were doing the augmented matrix, and you knew that you did the augmented matrix. That's really what most of it came down to.
Okay.
There's some finer points that maybe you got and maybe you didn't. But if you got that much, it's enough to go on, and we'll figure the rest of it out. When it comes up, I'll scan it and comment on it and email it to you.
Okay.
Okay? And I apologize for that, but my entire flow of paper got screwed up all last week, so no excuse, but it did. Okay, so every vector is orthogonal to the row space. Okay, so that's something we know. That's something I ask you to test. Ask you to find the null basis for the null space and a basis for the row space, and show that all those vectors are orthogonal. Okay? And that's just a matter of taking their dot products, because I did it in Euclidean spaces. Okay? Okay, well, over here, we get the column space. And I'm doing this in terms of transformation T. The transformation is T and it's represented by matrix A relative to some basis of this space and some basis of this space. In practice, so far, it's been standard basis of Euclidean space, but it doesn't have to be. So when I say n of t in row space of t, I should really say n of A in row space of A. T would be okay here because a null space of T is a null space of A. But when you start talking about row space, you'd better have a matrix, not a transformation rule. It isn't a matrix, okay? And we established a long time ago that any linear transformation can be represented by a matrix. Whatever the rule is, put it in the matrix. You've had problems of that nature. You've done those. Okay. So anyhow, now we can talk about this. And what we get here is the column space of your A matrix. Okay? And the thing about this column space is your whole vector space V maps to vectors that span this column space, that are in this column space. Okay? So all the vectors in V go to your column space. Okay? And this is the image of V. Column space is the image of V. All the vectors of V go into the column space, and there's nothing in the column space that's not in V. Okay? Now, they didn't come from V under the transformation. And then you have should have made this wider. I'll write it a little bigger. This is a null space of A transpose. Okay? And it's the set of vectors in here that don't come from anything over here. Okay? So this is a set of vectors in W that aren't images. The vectors in A.
So wouldn't that just be everything outside of the column space of A?
Yeah. And that's exact. So these two things partition this space. Okay, there's a partition. The column space is one side of the partition, the row space is on the other side. Okay? Also, you can then represent this as what's called a direct sum of vectors, column space, and null space of A transpose. Okay? But we'll talk about direct sums separately. It's a really important idea, really big concept, and it was on your test, but it wasn't called that, and everybody screwed it up. So we'll address it. Okay? Nobody seemed to know what I was asking. Well, that might have been one of those where my problem didn't make any sense. So maybe there's a good reason for it. We'll see. Maybe I'm the one that screwed it up. Okay. The column space is the image of V, and the column space is also the row space of A transpose. So you call this the column space of A or the row space of A transpose. And why is that? Well, the columns of A are the rows of A transpose, so the span of the vectors, the columns of A, is exactly the same as the span of the vectors of the rows of A transpose, okay? So, very simple. And I will say, and you want to start digesting this idea,